Hello, guys. Hope you guys are all well and safe. Tonight, Middlesex University Product Design Engineering, and Design Engineering are really excited to host the fourth talk in our annual guest lecture series, which runs weekly throughout the academic year on Thursday evenings. Tonight, we're really excited to host Simon Gwozdz, all the way from Singapore, CEO and founder of Equatorial Space Systems, with a talk titled The Tesla or Rocketry, How ESS Revolutionises Space Access. So details of Simon and the talk were sent to your emails ahead of the lecture, including links to social media pages like LinkedIn, Facebook, alongside the Equatorial Space website as well. So feel free to connect with Simon online. And Simon, it's all yours, ready to go.
All right, thank you so much. So yeah, thank you for the introduction. Great to be here. Thank you very much for the invitation to share more about our work with you guys. And essentially what we are working on is rocket systems which are simpler, safer, and more cost-effective compared to anything else available in the market right now. For those of you who are not too familiar with recent developments in the space tech industry, well, satellites are getting smaller, satellites are getting cheaper, and they are getting more accessible. And that is driving a massive market demand for agile launch opportunity. And by agile, I mean launch services which offer specific access to specific orbits and are also responsive to the client's schedule. So this is essentially the market which we are currently involved with. So, okay, is it okay if I screen share?
Yep, that's totally cool. You can go for it.
Ahmed? All right, perfect. Okay, can you guys see it?
Yep.
Okay, so the future of rocketry is, well, I dare to say, drastically different compared to what we are seeing today. And you know, before we actually jump into the whole idea of space and rockets and launching of satellites, you know, for us as long as we are still, you know, keeping our feet on the ground, let us talk not about rockets, but let us talk about cars and automobiles in general. And we've seen some really exciting activity in the automobile landscape. In the past 20 years, we've seen the first major car maker emerge with a completely different approach to what was traditionally done. And of course, no, sorry, my slides got a little scrambled. And of course, that's Tesla. And the funny thing about Tesla, I mean, really impressive, in fact, is the specs you get for the price. If you look at Tesla Roadster, that thing is going to get you from 0 to 100 km per hour in less than 2 seconds, which is faster than Bugatti Chiron, right? And the catch is that Bugatti costs you $3 million, and Tesla Roadster that's coming up is tentatively priced at $250,000. And now you might be wondering, how is that even remotely possible, right? And it really boils down to the technology and its simplicity. So if you look at Bugatti and internal combustion engines, well, they are madly complicated. You guys are the design students. You know how complex, you know, engineering design can really get, and especially things like internal combustion engines. You know, they really boggle my mind every time I look at them. Compared to that, Tesla is, well, very straightforward. It only has a few electric motors and the battery pack, and that's essentially the baseline for the drivetrain. And that is, well, lighter, it's simpler, it's, well, aside from the batteries, of course, it's cheaper to make. And this is basically the same effect that we want to achieve with rocketry. So I'm not sure how much do you guys know about rocketry, but let me give you a little crash course in rocket science, you know, to the best of my ability right now at 1 a.m. Singapore time. So all rockets carry oxidizer and fuel. That's what they mix together and combust together to produce thrust. And thrust is needed to build up velocity. Velocity gets you above the atmosphere. That's the first step. And after that, you have to continue burning your engines until you build up sufficient velocity to actually enter an orbit, if that's your goal. So in case of solid rocket motors, you can think of them as giant firecrackers, essentially. You premix oxidizer and fuel. One of the most common combinations of that is this rubbery substance called HTPB, hydroxyl terminated polybutadiene, mixed with ammonium perchlorate, which is the solid oxidizer. So essentially, it's a very straightforward system. At the center, you will have this thing called the port, which you can see right over here. And that is where the combustion takes place. And that's where the exhaust gases are being produced. And later, they are just driven through a typically convergent divergent nozzle, at which point you basically produce choked flow, and therefore you achieve supersonic exhaust gas velocities. So it's very simple in its principle. The problem with solid rocket motors, which are quite often used in commercial applications, is how dangerous they really are. We're talking high-powered explosives. In many cases, we're looking at at tens or even hundreds of tons of high-powered explosive. So even though solids are simpler compared to other kinds, they are not necessarily cheaper. And a fantastic example is actually a European launcher called Vega, built by the Italian company called Avio. So Vega costs around 40 million euros for launch, and it only carries around 1.5 tons of payload, and it's basically almost as expensive as Falcon 9, which carries almost 20 tons. So even though solid motors are simple, they're also dangerous and also inflexible. There is no way to actively throttle them in flight. You can do some tricks by adjusting the geometry of that opening in the center, which we call the port, and therefore modulate the surface area exposed to combustion throughout, at various phases of the burn. But there's no way to actively throttle that if you need to do it in flight. Also, it's very difficult to shut them down. It's theoretically possible. Some ballistic missiles, I believe, are capable of doing that. Essentially, you have to blow off a hole in the entire engine housing to achieve this blow-off effect and reduce pressure until to the point when the combustion actually stops, which is not very practical for commercial companies, especially ones which are working with unlimited budgets. It's just really, really not as easy as it seems. On the other side of the spectrum, we have liquid fuel rocket engines. And the principle of operation for those is that you carry oxidizer and fuel, as the name suggests, in a liquid form. A very common combination is liquid oxygen, abbreviated as LOX or LOX, and kerosene, a refined form of kerosene, basically. So to actually supply those things into the combustion chamber where the explosion takes place, and therefore the exhaust gases are produced and directed through the nozzle, there are two ways to redirect, to deliver those substances, either through a pressure feeding system, which requires much more robust tanks, which can actually survive substantial pressures, and they are therefore heavy, and it's not a good idea for a rocket to be heavy. Or more commonly, for at least first stages and so-called boosters of launch vehicles, you'll typically see a very, very complex turbopump machinery. In fact, that is the most expensive part of a liquid fuel rocket engine. A typical turbopump will set you back by at least $500,000 if it's lightweight enough to be rated for flight. And well, the beautiful thing about liquid propulsion is that it's very, considerably more flexible. A liquid rocket engine can be throttled, so it can be used for more than just this first initial phase of flight when you're just building at velocity like crazy. And it can also be shut down or restarted if the design allows for that. Majority of companies developing small launch vehicles right now are working with liquid fuel engines. Of course, they are really complicated, and therefore it's not cheap to really build them and get them to work in a reliable manner. But this technology is quite well established. So we can think of this as really your internal combustion car. It's an established technology. There is in certain countries like the US, there is a lot of expertise in building them, but still they are not cheap. They can be made better, and they are still susceptible to a lot of things which can go wrong. We're talking about lots of moving parts here. You guys are the engineering students. You know very well how difficult it is to get something with a lot of moving parts to work reliably. So therefore, they are not a perfect solution either. So what fewer people are aware of is existence of a third type of chemical rocket engine, which is called a hybrid. So in a hybrid, as the name suggests, you basically deliver liquid oxidizer to a combustion chamber where the fuel is already stored in a solid form. And then that is basically when the combustion takes place and when the exhaust gases are produced and directed much the same way through a convergent divergent nozzle. So the idea here is that both of these substances are stored in two different states of matter. And what this gives you is a system which is fundamentally non-explosive. The solid fuel itself is inert. It's very straightforward to manufacture, very straightforward to transport and store, and it's safe to operate. That is the biggest advantage of hybrid rocketry. And yeah, as you can see, in theory, all you need is really a valve to control the oxidizer flow, and as a result, you can control the throttle, or you can shut it down if necessary. In fact, NASA was exploring use of a hybrid for this space shuttle solid rocket boosters, but they couldn't really get it to work because of the fuel technology limitations, which were previously affecting this kind of propulsion architecture. So this is something which we'll be getting to shortly. But first, let's take a look just how safe hybrids are compared to other kinds of rockets. I know this is not the best thing to show to people, rockets blowing up, but it will really prove the point. So this is Falcon 9. That's in 2016. What happened here? The pressurizing helium tank, which was inside of the oxidizer tank of the upper stage, just came loose. It basically pierced through the engine, through the second stage skin, and you can see what happened yourselves. It basically just blew up on the spot immediately. So yes, liquid fuel is still quite risky. There's still a lot of things which can potentially go wrong, and when they do, it's typically very explosive. Conversely, right over here, we see an example of a solid rocket motor explosion. That's a Delta II. It's a NASA-built rocket based in not built, but operated rocket back in the 90s. So you can see this stop footage, and yeah, you can see just how quickly this explosive effect is actually taking place, and that's basically it. So yeah, doesn't really inspire a lot of confidence, I know. So this is an example of a hybrid. It's a company called AMROC, the American Rocket Company. They were one of the pioneers of commercial use of hybrid rocket motors, and you can basically, what happened here is that they had this additional supply of hydrogen peroxide for thrust vectoring control. Basically, they would inject it straight into the nozzle to add a little extra moment in terms of the flame geometry coming out of the nozzle, and therefore control the direction of the flight. Unfortunately, their valve got stuck. There was an excess amount of hydrogen peroxide just burning through the motor, and at the same time, basically the oxidizer flow was also stuck, and the rocket thought it was in flight, and that's why you can see all that hectic attempts at thrust vectoring. They were using liquid oxygen. Their valve got basically froze up. As you might know, liquid oxygen is really cold, but you can see, even though it's burning up, you can see that black smoke. That's basically the engine housing and the insulator are already on fire. It's not actually exploding. And even, granted, that thing basically topples over at the end, but the damage to the launch structure was in the order of a few $1,000s. Unlike in case of SpaceX, in which the facility had to be fundamentally revamped. So even if something goes wrong, hybrid is what you really want to have. It's simply not as explosive. So yeah, you can see even after it topples over, it still doesn't blow up. It's just like just a piece of inert material on fire. So now you might be asking me what many of our investors are initially asking: if hybrids are really so great, then why is not everyone building them all the time, right? I think you can somewhat see where I'm getting to, with this earlier comparison with electric vehicles. There are some inherent advantages to building a hybrid. It's simply simpler and not as not as prone to multiple kinds of malfunctions as internal combustion engines really are. So this is where we're getting slowly to, towards right here. So let's look at the fuel options which were traditionally available, and how do we solve that entire problem. So if you take things like HTPB, which I mentioned earlier, which is very commonly used in purely solid rocket motors, and if you don't mix it with an oxidizer, and if you just use it as a fuel for a hybrid, people have tried that, people are still trying that. And well, the problem is it doesn't burn very quick when it's not mixed with oxidizer, because the combustion only happens at a very thin film layer inside of the port. And of course, if there is no oxidizer premixed into it, it doesn't really expand very quickly. We call this the regression rate of the fuel. So one of the ways that companies and organizations alike try to overcome this problem with was by adopting those very complex geometries of ports, have multiple openings running through the entire length of the solid fuel. And the idea was that if you do this, you are going to have a greater surface area exposed to flame, which makes perfect sense, right? Unfortunately, this leads to a number of issues. So the first issue with this system, with this kind of approach towards traditional polymer fuels such as HTPB, is, well, it basically reduces the volumetric efficiency of the rocket. You have to increase this, the cross-sectional area of the stage to accommodate the same amount of fuel, and that induces extra drag. Again, not a great thing to have in a rocket. Second problem is that to maintain structural integrity of the solid fuel with so many different openings, with this cartwheel configuration, if you will, you have to use a support structure inside of it, which not only increases the mass, which is again a very bad thing for a rocket. You want to be as close to perfect ratio of dead weight to actual fuel as possible. It also impedes with the actual combustion effect, right? Basically the combustion layer, that film which is actually burning, is impeded by the support structure, and therefore you actually have a lot of leftover fuel at the end of the burn. And if you're building an amateur rocket or an academic rocket that's just supposed to go up and down, you can live with that. But if you're trying to build an orbital launcher, if you suffer from loss of fuel to the magnitude of 15 to 20%, you're not making it into orbit. You're not going to build up sufficient velocity. Right, I just realized I skipped a little important element, just for those of you who have maybe slightly less, exposure to fluid mechanics and, engineering as a whole. The problem with lower regression rate is that you suffer from lower mass flow rate. Less fuel basically burns up and gets ejected through the nozzle, and that affects the thrust, and thrust affects the thrust to weight ratio. So in case of a single port configuration, this simply doesn't produce enough thrust. That's the issue with it, and that's why there have been those attempts to resolve that by increasing that entire surface area exposed to combustion. So this didn't really work quite well. It could be done, but it would not be a very efficient rocket. You have to have something which is drastically oversized for the amount of payload you want to carry. So some institutions decided to give a shot to paraffin wax, literally paraffin wax as the solid fuel. And again, paraffin wax is very easy to procure. It's safe to handle. It's available anywhere in the world. Even in Singapore, there is absolutely no problems procuring any of it. You might know how restrictive Singapore really is in terms of explosives and anything really. And the problem with paraffin wax was the combustion stability. So paraffin wax liquefies itself, which was the very objective of using it on the first place, because that increases the regression rate, and therefore you do have a higher flow rate and therefore a higher thrust. Unfortunately, paraffin wax doesn't bind into anything really, and it's also and because of this, because it doesn't really hold its own structure very well. The moment you expose it to heating, it starts to slump and change its entire geometry. And when paraffin wax changes its geometry, when basically when you start having this entire slumping effect going on inside of the engine, you will start to experience mass ejection of the fuel. So for a different reason, but you are still going to end up losing around 15 to 20% of your solid fuel. In this case, not to the sliver, as in case of polymer fuels, but to the fuel just flying out of the engine uncombusted, right? So that's a big problem. Not only it reduces your efficiency, it also introduces a lot of of thrust fluctuations, which is another very bad thing for the entire rocket and the payload. So there are some ways to try to basically improve that structure integrity with paraffin wax. You can premix it with some other substances, but then again, you start losing regression rate, which defeats the entire purpose when you do that. Also, paraffin wax shrinks quite a lot when during the curing process after it's being casted. So to avoid any cracking or any undesirable effects on the geometry of it, what you have to do is basically use this process called the rotational molding. And rotational molding essentially involves like a centrifuge, which basically just keeps spinning until the whole thing just settles in place. And if you try to mix it with anything that's energizing it, like aluminum powder, again, very commonly used in rocketry, it's very, very difficult to get it evenly distributed in this system. So again, paraffin wax did not exactly solve that problem, even though there's been a number of experiments trying to tame paraffin wax. No one has been successful so far. And just to give you an idea, about so as you can probably imagine, we basically developed our own fuel combination, which is our core IP, and this is why we are confident we can make hybrids work, and therefore we can become the Tesla of rocketry by introducing a system which is much simpler and fundamentally effective compared to what's been done before. So this is one of our previous engine tests which we have done. It's a pretty small motor, but you can see that the flame geometry, the shape of that entire plume doesn't really change a lot. It's very, very nice and stable. We did have some, we can see some sparks here and there. That's because we used a very substandard aluminum powder. I can disclose that, but because that's not the core chemical composition that we are using. That's just an additive. And well, it's nice and stable, and we have thrust curves to prove it. This is what NASA has been doing with paraffin wax. This is the Peregrine Motor, which was built by the Ames Research Center in California. And you can just take a look at, just be your own judges. Not sure how, if it's lagging or anything through Zoom, but you can see there's a lot of instabilities going on. And even though NASA spent close to a decade developing all of this and trying to get it to work in a reliable manner, they just couldn't do it because of natural tendencies of paraffin wax. So this is really the core change that we are introducing compared to anybody else. Our fuel, depending on the oxidizer delivery system that we use, produces performances very comparable to that of solid and liquid fuel and fuel systems. We only have around 4% leftover fuel at the end of a burn. It's structurally stable. We can only use one single port, and we don't have to worry about slumping effect, and the regression rate is high enough for us to do just that. We are actually using a non-cryogenic oxidizer to go with that, nitrous oxide. We'll be chilling down to around minus 60 degrees to densify, to close to liquid oxygen density levels. And as a result, we have a system which is actually scalable all the way into orbital grade launchers. And this is really the core differentiator that we've got. And let's talk a little bit about the complexity of what we are working with. So I know this is a pretty extreme example of what a liquid fuel rocket engine looks like. This is what SpaceX uses on the Falcon 9. It's rocket science. It's crazy complex. It's an open cycle engine. You can see those little nozzles sticking on the side. This is basically a piece of, that's known as the gas generator right over here. It takes a little bit of oxidizer and a little bit of fuel to basically spin the turbine, which supplies the main feed lines with under correct pressure. It's really not easy to build that stuff. But let's look at slightly more relevant examples. So this is what Rocket Lab, a New Zealand company, is using on the Electron launch vehicle, which is operated currently from New Zealand. And their key innovation was, they had the right idea. They wanted to simplify the whole thing. They were successful with it. Instead of a turbo pump, they decided to go ahead with an electric pump. That was their key innovation. But take a look at our design. Compared to hundreds of thousands of parts for Rocket Lab, which is already quite straightforward, we're looking at using fundamentally less than 20 individual parts, minus the thrust vectoring system, of course. But it's going to be very, very straightforward. We are currently developing this full-size motor, and we'll be using a block of 4 of them for our launch vehicle, which is going to be comparable in capacity to what Rocket Lab is doing. To give you a little extra idea, what can we do with this technology, and how does it compare in terms of development costs and the price point? And this is a very, very generous budget. We are confident we can complete the entire R&D for substantially less than that. So Rocket Lab spent around $120 million developing the Electron, which is already not bad at all, especially for people who still dwell on the Apollo era budgets. So they've done a fantastic job. That's as cost effective as a liquid propelled launch vehicle can really get. They can carry around 120, 140 kilograms into low Earth orbit, depending on inclination and altitude. And they're pricing this at around 6.6 million USD right now. We're going after the very same market niche. So very similar payload capacity, but our development costs will be basically one-fourth of that. And the price per launch will be substantially lower as well. We're looking at 4.5 million, and that's, that actually includes a very healthy profit margin. So thanks to the technology, we can produce a much more compelling product. And this is where this is why I like to compare ourselves to Tesla, really, in that sense. So also, just to give you an idea where the hell would we be launching from, Singapore is close to the equator. It's a good place to launch orbital rockets from. You get a little extra payload capacity because of the additional rotational velocity of the planet at this point. And at the same time, you actually get to launch in any direction, into any orbital inclination as you wish, which actually allows extra flexibility to clients. Sea launching has been done by a number of entities before. Recently, the latest entrant to that is actually China. What you can see on the lower right corner over here is the Long March 11 launcher. They've been doing those tests in the Yellow Sea. And well, in our case, that's really an added bonus, but the core of the whole deal is really the technology. So where are we currently? So this is what we call the low altitude demonstrator. The motor firings that you saw just now is for this particular thing. It's designed for a pretty modest apogee, but we did it on a really low budget. So it's really just a stepping stone for fundraising. All right, and yeah, just to link back with the example on the first place. What SpaceX and Rocket Labs are doing are the internal combustion engine cars. Complex, but very well established. And what we are working on is a little like an electric vehicle. We did not invent a hybrid rocket motor. We don't make that claim. But electric, and neither Tesla invented the electric cars. In fact, electric cars have been around since the 19th century. Everybody knew their potential advantages in terms of simplicity and mass. And the problem was always the battery technology, the energy density, which affected of course, power output and the range. And that's where the key innovation really came from when Tesla came around. Usage of that novel battery technology to produce competitive electric vehicles. And HRF1, which is our solid fuel, essentially is to hybrid rocketry what lithium-ion batteries are to electric vehicles. That is the value of what we've got, and we plan to take it all the way and develop a company which will compete with the biggest and most established players in the launch landscape. We can do it. We have a strong differentiation, and we will produce rockets which are safer, simpler, and more cost-effective compared to anybody else. So if you're interested in staying in touch, we are currently not hiring. We are still fundraising, basically. So unfortunately, this has to wait a little. But we are keeping a register of interested people. So if you'd like to get involved, do add me on LinkedIn. Do follow us on social media, and do send us your CVs to careers@equatorialspace.com. We might be doing more work in the UK coming up in the near future. In fact, we're looking at it as one of our potential bases of operation. And well, looking forward to meeting you guys. And thank you very much for your kind attention. I know it's a pretty chunky presentation, but I don't think we can explain this in any simpler terms. and I'm looking forward to your questions.
Amazing. Thanks a lot, Simon. That
Sure,
was
thanks.
super interesting, and thanks for the science behind the rockets as well. Just a question. When I was reading your biography earlier, how did you get into propulsion and propulsion systems?
Okay. Yeah, I get this question a lot. So I think there are two answers to this. First of all, I really have to blame Tom Hanks and Ron Howard. I grew up watching Apollo 13 on a loop. I don't know how many times I've seen that movie, and it just really never left me. And I think everybody has a phase in their lives when they are quite fascinated with rocketry and space. It's just that some of us refuse to grow up, really, and I'm one of them, clearly. But yes, to give you a little more in-depth, back origin story. So when I started university, I was actually not from an engineering background, but I decided to basically start to self-study the fundamentals behind propulsion and behind orbital mechanics. And at the same time, I began to volunteer with a local space industry association here in Singapore. And I could actually speak to people developing satellites. I could validate some of my ideas, get a lot of corrections along the way, based on their real life experience. And as a result, the idea for Equatorial Space was born. I'm not the engineer myself. In fact, we have one of the top propulsion engineers in hybrid propulsion worldwide, Mr. Jamie Anderson. He's got 30 years of experience working on those systems, and he's the inventor behind HRF1. So, I also don't want to misrepresent myself that I came up with all this stuff. I did not. I was just lucky enough to rope in the right people to put together a crack team.
Amazing. Thanks for that. A few questions coming through in the chat as well. If you were to hire someone or give an internship, what would you look for in a candidate?
Okay, very good question. So, of course, bulk of what we do is in one way or another involved with either hardware engineering in terms of like PCB design and integration of various electronics. Of course, mechanical design. And there's quite a bit of software as well for engine controls and for the GNC, the guidance navigation control element of it. But that said, I do know people who have been from slightly different backgrounds, like from material science, from general design fields, who learned the necessary relevant knowledge pretty quickly and were able to contribute in very meaningful, in fact, some key ways. I would say the most important quality that we are looking for in people is, well, being able to solve problems on the fly. So any form of hands-on experience is invaluable. Some of the best engineers I have on the team have been involved with things like race car development back in university. So aside from their coursework, they had a lot of experience with like actual hands-on problem solving. I think that's the most important quality.
Amazing. And all of the guys in the room, that you guys do a lot of learning through doing and through experiential practice, right? So like hopefully that philosophy will translate in terms of being able to adapt and be flexible. And yeah,
that's right.
Another question
Absolutely.
coming through from Demi Banjo is what quote do you live by as a rocket scientist?
Okay, so again, I'm not a rocket scientist. I'm an enjoyer, if not a casual fan, and really a full-time founder of the startup. But I would say Robert Goddard. It's difficult to say what's impossible because what was impossible yesterday can be a reality tomorrow. I'm paraphrasing this, but you really have to look into the future in this field. It takes quite a long time to get to the to the launch pad.
No pun intended there.
Yeah. That's absolutely right.
Samuel Cabrera mentions, what would you say is the most favorite thing about your position and your job?
Oh, wow. I would say in the normal times is actually the opportunities to meet really incredible people when traveling and conferencing and networking with people. I had a chance to meet Tom Mueller from SpaceX, the chief engineer for SpaceX, which basically built all of the rocket engines. That was an incredible experience. He was such a gentleman and such a kind person, really. And I get to, I would say this is really the favorite part. And of course, okay, second favorite, the absolutely best part. No comparison. We haven't done that, in the last few months for obvious reasons, but it's the engine testing, or soon test flights as well. For those of you who have not had a chance to actually witness a rocket engine test even on the ground attached to a test cell, I suppose majority of us, haven't had the chance just yet. Once you hear that sound coming out, once that shockwave hits you, it's just incredible. It ruins you for life. There is nothing else that comes close to that. Even with a pretty small rocket engine, it's just so powerful.
Awesome. And Luca Trebullo, he mentions, what's the difference in payload capacity between your rocket, which would set you back at 4.5 million, and the other one that's priced at 6 million?
Okay, Luca, now we're talking. So we're looking at pretty much the exact same capacity as the Electron. So the price differential will be, proportional to that launch price, because we're looking at a very, it's a substantially lower price per kilogram in this sense. But that said, we might be able to price it lower as we continue scaling up production. Of course, economies of scale is a huge consideration in terms of mass manufacturing of simple rocket motors. So we might be able to drop that substantially lower.
Amazing. And Brady Hansen, feel free to go live. You wanted to ask a question live, feel free to unmute yourself, and there you go.
Yes, thank you for the talk, Simon. Really appreciate it. I just was wondering what your sort of like testing, research, and development process is like as you go through different chemical mixes or different, mechanisms for valves and flow. Like what I mean, okay, I know you can get really specific, but what's your development process generally like? Okay,
so for the fuel, I'd rather not disclose too much because it's a proprietary, trade secret composition. But Jamie was the one to develop that, so he'll be really the best person to ask. In our case, the baseline fuel composition is already in place. So once we settle on a development process, we have the key parameters which are already known, such as the pressure coefficient and the regression coefficient. So once you know that, you can actually do a very straightforward modeling of how wide does the port have to be, how long does it have to be, and how many seconds do you have to burn this for to produce sufficient performances and sufficient impulse. So once we have this very basic analytical model, which is basically, it can be done in a spreadsheet actually, it's really straightforward, then we jump into the design phase. So of course, when it comes to the like valve design and the oxidizer delivery system design, it's very heavy on the Bernoulli principle. So again, it's nothing that's outside of a scope of maybe postgraduate kind of person to really get a grasp of. And of course, we have to validate things during what we call cold flow tests. So once we have the entire oxidizer delivery system in place, which is designed for a specific motor, for a specific flow rate and supply pressure, then we basically have to conduct a number of tests to make sure that we are basically discharging things at the correct rate. So the best way to really go ahead with this is by using a Coriolis flow meter, which we currently don't have because they are pretty expensive. But if you do that, it's pretty straightforward to characterize the injector and introduce any necessary modifications to it. And once you're confident with the performances of the oxidizer delivery system, you can jump straight into not straight into, but you can move towards hot fires. So that's where fun really starts. We basically bring those units into a secluded enough location, and we basically run the entire sequence with the ignition going on, and that's when we are actually able to test the thrust by determining what's the mass differential between before and after. And by measuring thrust, we can determine what's the specific impulse. Essentially, what's the exhaust gas velocity. So, so it's a pretty straightforward arithmetic at that point.
Great, thank you.
Amazing. And Vladan Gerbic, he mentions, and he asks, why do you think big companies may be reluctant to embrace new technologies?
Yeah, so, okay, that's really, that's largely caused by the fact that, it's not impossible for a big company to come up with what we did, but they are pretty confident and pretty comfortable with what they already have. Ultimately, if you're NASA or if you're Lockheed Martin, then you really have something that's already working. So there's this lack of incentive to actually create something that's more cost effective, because you already have it. Another problem with larger companies is, especially in context of the defense ecosystem, and space tech is very closely related to defense ecosystem, is the contracting model, really, the cost plus contracting, which further disincentivizes innovation and cutting costs, because you don't really have to worry about that. In fact, the more costs you add up to your program, the better. So that's another consideration. In a specific context of hybrids, the reason why HTPB was one of the commonly experimented with fuel is really the established supply chain. It's just already there. You don't have to develop any new supply chain to manufacture a different kind of, in this case, fuel, for instance. So it's really the confluence of an established supply chain, of the experiences and expertise of the core engineering staff, which is already comfortable with what they know and probably slightly reluctant to change that. And as well, and also it's a matter of the business strategy that company really takes. If you're a small startup, you want to jump into the market as quickly as possible and innovate if it means that you can reduce costs. If you're a conglomerate, you don't have to do that.
Amazing. And Aurel Marianne asks, is there a place where we can find the information that was mentioned in this presentation? Like, is there a shareable PDF or a YouTube channel or on your website?
Okay, so yes, some of the core information are on the website. Of course, we don't talk about Teslas over there. We don't currently have a YouTube channel, but we have the firing videos over at our Facebook, Twitter, Instagram, and LinkedIn pages. So you can stay in touch with us, and basically the high-level information is already included over there, including the innovation strategy pertaining to our solid fuel.
Awesome. And a question from Farhad Khan. He's seen a company called Relativity who makes 3D printed rockets. What's your view on 3D printed rockets? And will your company like to do this?
Yeah, so Relativity is actually one of the most prominent examples of something that started as a pretty small company and grew to a substantial size. They're based in LA, and yeah, so this is actually a very interesting example of of the kind of innovation strategy that many companies in this field currently are actually following. There is actually more than 120 different companies, which at least expressed an interest to develop launch systems right now, because the market for launch is just so huge. But you can see that very few of them introduce any substantial innovation in terms of the propulsion architecture. Majority of them, and Relativity is the absolute flagship example of that, are focusing on the manufacturing. And additive manufacturing, it does have quite a bit of potential. In fact, Relativity's main motivation is developing technology that will allow manufacturing of rockets on Moon and Mars. So that's why they are so hell-bent on making the entire thing 3D printed. In our case, we don't really see a reason to do it. In our case, we'll be very dependent on processes such as filament winding for the compressed gas over wrap tanks. We will most likely end up 3D printing some of the flow control system components, especially the injector elements, which require a high degree of precision. But for the rest of the structure and the rest of the entire system, we just don't really see a need for it right now. It's our systems are just easy enough to manufacture with subtractive methods right now. But I do think that the 3D printing is a very promising thing, and it's something that we are currently exploring as as we move forward.
Amazing. And Mohammed Alim, he asked a question: have current rockets at that scale considered nuclear reactors as a source of electrical fuel?
Oh, yeah. So you might be referring to. Okay, so rocketry is actually split up into a few different categories. So when it comes to burning things chemically, like oxidizing fuel to produce thrust, that's what we refer to as chemical rocket engines. And they are furthermore split into liquid, solid, and hybrid. And there's also monopropellant thrusters, which are just running a specific gas through a catalyst to cause this exothermic reaction in them. Nuclear propulsion is an interesting concept, but it's more on the electric side of things. There's in fact a few different ways to use a nuclear reactor on board. One of them is just to superheat a gas such as hydrogen to generate much higher chamber pressures compared to what a chemical rocket engine can produce. But unfortunately, I don't think they will be very practical in terms of their thrust to weight ratio. So they will be amazing in orbit for things like interplanetary transfers. They would not be very practical for launch. So I think launch will still remain the territory of chemical propulsion, really. There is another way to use a nuclear reactor, and that's basically by fueling, a Hall effect thruster or any form of electric thruster. I know absolutely nothing about those, so sorry to disappoint you.
Navpreet mentions you mentioned that you're currently raising funds for your company. So
yep.
where do you raise funds from? Who do you mainly get your source of funding from, and what's the process?
Yeah. So, oh my goodness. Yeah, this is basically part of my job. Yeah. So we've had some investments from angel investors, which are essentially private individuals who are interested in a specific industry, and they do see a potential in a particular business and its technology. And currently, we're actually in the process of raising our first institutional round from a venture capital firm, which is just exponentially more difficult. They require plenty of substantiated information pertaining to the budgets, pertaining to the valuation of the company, pertaining to market research, and ideally also they would like to see revenue and market traction. Which in our case is a little early, but we are discussing our first commercial contract right now with a European client for a suborbital rocket, which we are developing as well. You may find out more about that one on the website. It's going to be ready next year. But essentially, yes, the entire due diligence process is time consuming. It requires multiple meetings, which all have different spin and different focus area. And if you're curious to find out about the human experience of fundraising, yeah, sometimes if it wasn't for the specific area that we are working on right now, I am tempted to just jump off a building. Whenever I go for an investor meeting, it's just not fun. It's like a job interview, but times 100.
Awesome. And a question coming in from Harry Miller Adams. He's asking,
okay,
what would you be doing if you were in our position now, in terms of getting that step ahead of everyone else?
Okay, so if you're looking at doing something in terms of space, in terms of entrepreneurship in space tech, okay, lots of people say that launch is really oversaturated right now because there's just so much activity going on. I'm not so worried because most of it is going to run into the same obstacles as everybody else, that comes with using heritage technologies. I wouldn't want to discourage people who want to start a launcher startup. I think there's still a lot of potential ways to innovate. We just don't know exactly where. And I've been discouraged really, and it's working so far. So if that's something of interest to you, then I say by all means give it a shot. Furthermore, away from launch, there is a growing interest in cislunar space right now, and the Artemis Accords, which were also signed by the UK, will offer a lot of commercial opportunities with the moon. Business to government kind of opportunities for now, and before they actually start being commercialized for business and individual users. I've recently seen news that Nokia was actually selected to provide mobile connectivity on the moon in the next 1 decade. It's absolutely insane. It's and incredibly exciting. And I think I would say people who are just getting started, I would say, if you're not already in a place like that, do move to a country with a very established space agency, with strong interest in research and in development of new technologies and in exploration of space, and look towards the moon and beyond. It's the point to really start doing that right now if you want to, if 5 years from now, jump into where the market will actually be right then, or within the next 7 years, for instance.
Amazing. Andres Yusuf Romero is asking, how can we come and watch the launch live?
Okay, I will try to stream it. I don't promise it's going to work out. The place where we'll be at is a palm oil plantation in Malaysia, pretty far away from any city. So yeah, I'm actually not sure what the quality of connection is going to be there right now. Maybe we could use Starlink for it, but I don't think they have licensing for ground stations in Malaysia yet.
Awesome. And Mohammed Alim, continuing his question on the nuclear reactor as a source of fuel, he said, why don't companies consider this as a source of fuel in space and use instead of using harmful fuel substances just for launch?
Yeah, so it really boils down to the thrust to weight ratios you get from nuclear systems. Now, actually, there's been quite a bit of work done on that. Even back in the 60s, the project called NERVA, I have no idea why NASA gave that up. It was really exciting and it was working very well on the ground. I think one of the concerns was really the risk of launching a nuclear reactor with fissile fuel. Launch segment in general right now has around 6% failure rate. It's not as safe as commercial flying, nowhere near. So I think the environmental concerns of launching, fissile material is just really quite a big concern. Yes, there are some, radioactive substances being launched on probes which go into deep space, but they are not reactors. They are basically just RTGs, what was it called? Radioisotope thermoelectric generators. They basically use slow decay of a substance to induce thermoelectric effect into the power collectors. And they do carry small amount of radioactive substance, but it's not anywhere near the grade that you use in a nuclear power plant. So I think even in case of a launch failure, it's simply not going to produce a lot of additional pollution, especially if it's spread around a large area. So yes, I would say, yeah, sorry, I sidetrack a little bit. Okay. Yes, so yes, you could use them in space. In fact, they will definitely be used in space at some point. But even for the upper stage, you're still trying to build up that velocity as quickly as possible, and therefore you still need a substantial amount of thrust to weight ratio. You need to build that within 5 to 10 minutes after the boost phase and actually enter an orbit. Otherwise, you're going to re-enter. That's why I don't see them useful even for upper stage applications right now. For transfers outside of low Earth orbit, definitely. I think there's a massive potential in nuclear propulsion. In fact, I'm a huge fan of that idea. I think if NASA didn't give up on that, who knows where we would have been by now.
Amazing. And Joseph Salem, building on that, he asks, in terms of using a nuclear reactor, would this involve plutonium in the process?
Yeah. So again, I'm not an expert in nuclear engineering. But yes, I believe so. It could be plutonium or anything that's currently used in commercial nuclear reactors, really. Yeah, so it would actually involve something that's potentially highly radioactive, which is a concern.
And Luca Trebio, he mentions that if a new kind of technology for propelling rockets popped up and it seemed to be better or more efficient than yours, would you keep on developing yours or start investing in a new technology?
I would say yes, I would keep on, because again, you don't know until it's actually flown. So even if something that's very promising shows up, and I do track activity in this business, first of all, there's no one-size-fits-all solution. Hybrids are great if you're building a cost-effective small launcher. It's not going to be the most effective solution if you're trying to build a heavy launcher with reusability in mind, like Falcon 9. But then again, it's like a lot like comparing, a Learjet to a 747. They are just working with different market niches. So that itself is is one of the reasons which I don't panic if someone new shows up. And if someone came up with something very interesting, I would keep my eyes on it. But I would, one of the jobs of a CEO is not to panic. Keep your eyes open, but keep steady, and have trust in your technology and your team. And if you really see something wrong, then yes, if at one point we basically really cannot get any more further traction because someone with drastically better approach showed up, then we would change our entire business model and look into something different.
Amazing. And talk Vidas, you want to go live if you're still around?
Of course.
Yeah.
Great up with this. Long time no see.
Hello, to see you. Look, so my question would be actually about the Starship. So the Starship, to those who maybe don't know about it, is basically super big rocket made by Elon Musk, by SpaceX, and the idea behind it is to bring us to Moon and later on to the Mars. But the unique thing about the Starship is that is most public development process of the rocket ever. We can see weekly updates from YouTubers about every single part of hardware which is put inside that rocket and the rocket facilities around. So my question would be, for you as a rocket developer, as an entrepreneur, and everything else, do you follow it, and what are your thoughts? Because ULA and other traditional American ones, they use this all the Paula style approach where you try, check before doing anything. And Starship seemingly use a Russian old style Soviet methods. Build, explode, build, explode. What would you use, and what is your advice for us as designers? What methodology, for not even for rocket projects, but for any kind of project, is better? To try and think, or actually do and explode things? Thank you.
Yeah, sure, man. So it really depends on the situation. I know it's a pretty it's a non-answer basically, but it really depends on your priorities as a company, on the kind of project you're working with, and the degree of confidentiality you really want to maintain. So ULA is a great comparison with SpaceX because they have a very meticulous approach towards developing and manufacturing the rockets and launching them. In fact, they have, I believe, if not 100%, and very close to a reliability rate very close to 100%, which is crazy high, basically. But they are very expensive as well. So what ULA really, where they position themselves is the prime contractor for sensitive missions. Whether sensitive from the national security perspective, because once you put together a satellite worth $1 billion, you really want to make sure it gets into orbit. And ditto for the for scientific missions for NASA. Again, scientific missions are on order of magnitude more expensive than commercial satellites. So for SpaceX, for instance, they wanted to be more cost effective, especially in the beginnings, because they did not have the kind of street cred that ULA had. But in the end, yes, Falcon 9 became the workhorse of the industry. They worked out. They actually got it, crew certified, which is incredibly difficult, and it worked in the end. They basically had to take this a slightly different approach to arrive at the same destination. Now, regarding Starship, I think the reason why they are very public with this is because of just how inspiring the project is. It's supposed to be our ride to Mars, to Moon and Mars, really, and it's just a part of their public relations strategy to keep it very open. Also, my opinion is that the success of Starship testing does not actually change their commercial standing, because it's currently not one of their lead commercial products. Falcon 9 is already very well established. So even if something goes wrong, it doesn't affect their contracting process for commercial launch with Falcon 9. So I think that's one of the reasons why they are so open and so upfront. I don't think any investor would be happy with a startup, or an early stage company being as transparent. I just don't see, that kind of situation being happening the same way as with SpaceX right now.
Amazing. Thanks a lot, Simon. Thanks a lot for all of the questions and your time. It's 2 a.m. now in
My pleasure.
Singapore, and you
Yes, it's been a long day.
during this era.
Okay, maybe just one last question. I like this one actually. Okay, so launching from higher altitude, will it help to reduce the fuel required to reach orbit? Okay, this is a great one. I love that question because there's just so many ways to answer it. Yes, so absolutely. You save yourself altitude and you get some additional velocity, which is why air launching is more efficient. Also, most importantly, and this is something that not many people are as aware, is air launching is actually very efficient in terms of the nozzle performances. You know, nozzles are much more efficient in vacuum because there is no ambient pressure impeding the exhaust gas flow, and therefore you actually produce a higher specific impulse and basically higher exhaust gas velocity and therefore ISP in at higher altitude. So actually you get up to save a lot of performances because of that effect. The issue with higher altitude is, unless you're somewhere in high mountains, like really high mountains, which does impose a logistical challenge, is that air launching is really expensive. And I was giving an example just now with Rocket Lab spending $120 million on the Electron. Virgin Orbit spent over 700 million USD so far on the Launcher One, which had one test flight, which was unsuccessful. Not really a shock. But yeah, it's way more expensive. We're talking about operating a fleet of aircraft, or at least one aircraft. Operating, maintaining the crew, maintaining the airframe, and getting it certified for flight on the first place, which is all really taking a lot of money. So yes, it can be done successfully. Pegasus, built by I think Orbital, back in the 80s, I believe, if I'm not mistaken, did become a very successful product. But yeah, it's really expensive. It also costs close to, I think, 40 million US per launch at this point. So yeah, it can be done. It does offer you a lot of benefits, but it's also just for practical reasons, it's basically very expensive.
Awesome. Thanks a lot, Simon.
Sure.
Again,
thank you. Thank you
us.
for having me.
So from all of us at Middlesex University, product design engineering, design engineering, thanks a lot for joining us. Thanks for your time. And yeah, we look forward to seeing the progress of and hopefully the launch of your.
Me too. I'll keep you guys posted. And yeah, thank you so much, everybody. And yeah, thank you so, and all the best.